Welcome back, friends. Today our topic of discussion will be bitwise operators. Now, before beginning with this bitwise operators, let me tell you this particular operator is actually primarily concerned with manipulation of the binary digits in a number. I believe you already know that every number representation inside a computer is done using a binary number system. Now basically when I talk about a bit, it is actually an acronym of binary digit. This is what actually happens. Binary digit. Now there had been a lot of demands from students who wants to understand how this bitwise operator works. So therefore I am going to give you an introduction on how the bitwise operator works, but I am going to keep things very simple, just assuming that you do not understand any of the number system. I have taken this into assumption that you do not understand any number system. If you already know the binary number system, you can skip the initial part and you can directly go for the bitwise operators. I assume that you have no idea how this binary number system works, and therefore first of all let me teach you how to convert a decimal number. Decimal number means a number which uses digits from 0 to 9. That is, there are 10 digits. 10 represents decimal. So it's going to use 10 different digits to represent a decimal number. When it comes to binary number system, which is used in computer, it uses just 2 digits, that is 0 and 1. Why they selected binary is because it is easier to represent the electronics inside a digital device. Whether it is computer or smartphone or any kind of electronic device, it is easier to represent binary numbers compared to decimal numbers, because we have to manipulate with only 2 digits, that is 0 and 1, hence the binary number. So now first of all we are going to learn how to convert a decimal number, that is the number which you have learned in mathematics or the numbers which you use in programming, that to binary. For example, if I have a number, say 12, and this is a decimal number represented by its base. You can see I have written it slightly as a subscript. So this is a decimal number and I am going to convert it to binary. So what we are going to do is, we are going to successively divide this number by 2, because that is the base of the binary number. Base of the binary number is 2 because using only 2 digits, that is 0 and 1, it is possible to represent a binary number. So hence the base is 2. So what I am going to do is, I am going to successively divide the decimal number by 2 and carry on writing the remainder. Look at this process. Suppose this is 12. So first of all, I divide it by 2. So 2 6 is 12, 6 is the quotient and the remainder happens to be 0. This side we are going to write the remainders. Next, we divide this 6 by 2, 2 3 is 6, remainder is 0. Then once again, 2 1s are 2, remainder is 1. So now, we cannot further divide it by 2. So we stop over here. So what we are going to do is, we are going to write all this, the first quotient and the remainders, we are going to write from bottom till the top. That means 12 base 10 in the form of binary is 1 1 0 0. That's the binary representation. Now what we are going to do is, we are going to do the reverse process, that is convert a binary number back to decimal. So this time what we are going to do is, we are going to take each digit and multiply it with its weightage. What do I mean by that? Let's see, suppose we have a number, say the same number 1100 in the form of binary. I am going to convert it to decimal. Remember, the base of decimal is 10. Now what we do is 1100, we extract each digit and multiply it with its weightage. That is, since it is a binary number, so the last digit will have its weightage as 2 to the power of 0. Next, 0, this 0 into 2 to the power 1. Next, 1 into 2 to the power 2. Next, 1 into 2 to the power 3. So what we get, this is 0, this is 0, this happens to be 4, this happens to be 8. When we add this all up, we get 12, which is the decimal number of this. You can see I have just interconverted 12 to binary, and from binary back to decimal, that is again we are getting back 12. So this is the technique of converting a decimal to binary, and similarly from binary back to decimal. See, this process is very simple. Now, why am I telling you this is because every number that you use in program is internally represented using the binary number system. For example, suppose I have a variable int a equal to 13. So when I tell a equal to 13, what actually happens is internally the number 13 is converted to binary. That is, remainder is 1, 2 3 is 6, remainder is 0, 2 1s are 2, remainder is 1. So 13 gets converted to its corresponding binary, that is 1 1 0 1. Now we know that the integer type variable occupies 32 bits. That is, there are 32 spaces to represent an integer. Now what actually happens is 13 requires only 4 bits to represent itself. So therefore the remaining 28 bits will be filled up with 0. For simplicity, we are only going to write the last 8 bits. So you see, in fact, all the remaining 28 bits are 0. So internal representation of 13 inside the variable a is actually this. This is what happens when you write int a equal to 13. And bitwise operator is actually going to manipulate these bits. We are going to see that slightly later. Now let us try to understand how negative numbers are represented. This is very interesting in Java. The representation of negative numbers. In fact, inside any electronic device, the representation of negative numbers is very interesting. Now, what they do is, the computer engineers, what they do is, they add a 1 to the extreme leftmost bit to indicate a negative number. You see, we cannot write minus because minus is not a binary representation of anything. So what they do is, they follow a very simple trick. They put a 1 at the extreme leftmost end of the binary representation of the decimal number to indicate a negative number. However, saying that, it doesn't mean that you are just simply going to put a 1 out here and this becomes a negative 13. No. So now let us understand how internally negative numbers are represented. It's a very simple process, however. So suppose I have the number minus 13 out here. Now look at the method by which we are going to represent minus 13. First of all, we are going to convert 13 as usual into binary. So 13 is there, we are going to convert it to binary, that is 1 1 0 1. For simplicity, once again we are going to write the last 8 bits. Now, Java follows a system called 2's complement to represent a negative number. So what we are going to do is, to find the 2's complement of this 13 to represent the minus 13, what we are going to do, first of all, we are going to find the complement of this binary representation of 13. To find the complement, what we do is, we write 1's complement of 13. Now 1's complement states that all the bits should be reversed. That means all zeros becomes 1 and 1's becomes 0. So what this actually happens is, this is 1 1 1 1 followed by 2 zeros. Again this is 1, this is 0. Just the reversing of the bits. All the 1 becomes 0 and zeros become 1. So this is our 1's complement. Now for 2's complement, what we do is, 2's complement, we simply add a 1 to the binary number. Now please remember the rules for addition of binary number. That is, 0 plus 0 is actually 0. And 0 plus 1, obviously it is 1. 1 plus 0, still 1. And 1 plus 1, very interesting, it is 0 and carry over 1. That means almost like 10 in decimal number system. But it's 0 and carry over 1. That is how we read it. So now we have 0 plus 1. It's pretty simple. It's 1. 1 plus nothing is 1. This is 0, 0, 1, 1, 1, 1. In fact, all the remaining bits all the 32 bits on the left hand side will be filled up with 1. Now you can see there is a 1 at the extreme leftmost end, indicating it's a negative number. This is what our minus 13 is, represented inside the variable a. Look at the difference. For positive 13, it was simply 1101, and when it comes to minus 13, we have all the ones on the extreme leftmost end and followed by all this. So this is how negative numbers are represented inside a variable using 2's complement method. So the method is very simple. First, get the binary representation of the positive number. Then we are going to go for 1's complement. In 1's complement, what we do? We just simply reverse the bits. That is, all 1's become 0 and 0's becomes 1. Followed by adding 1, which is actually 2's complement. In 2's complement method, what we do is, the 1's complement number which we generate, we add 1 to it to get the 2's complement number. And that is the negative representation of that particular number. Now, what we are going to do is, we are going to actually learn the different bitwise operators. Let me categorize them first. Okay, now you can see these are the different categories of bitwise operators. These are the basic bitwise operators, that is AND, also called bitwise AND. This is or bitwise OR. This is XOR or bitwise XOR, and then we have NOT or bitwise NOT. Along with that, we have a subset of the bitwise operator called the shift operators. And this you can see the less than symbol together, it forms the left shift. This is the right shift, that is 2 greater than symbol. And then we have 3 greater than symbols, which is called unsigned right shift. Now first of all, we are going to begin with, now before beginning with anything, let me tell you, these 3 are actually called binary bitwise operator because it works with 2 operands. And this is called a unary bitwise operator because it works on a single operand. So this should be clear. So first of all, we are going to begin with the binary bitwise operator, that is AND, OR and XOR. And then we are going to see the NOT bitwise operator. Now let us see what is this all about. I have taken 2 variables A and B, which is initialized with 86 and 66. You can see over there. And here inside the variable C, I am using the AND operator, that is bitwise AND operator, to manipulate this A and B. So A and B, and inside D, A bitwise OR B, and E is A bitwise XOR and B. So you can see all these 3 operator works with 2 operands, hence it is called binary bitwise operator. Now I have already found the binary representation of the number 86 and 66. So what we are going to do is, A, which happens to be 86, is represented in this format, that is 1 0 1 0 1 1 0. So there are total 7 bits. We put a 0 representing the last 8 bits. Now we have B, which is initialized with 66, and the digits are 1, 4 zeros, 1 0. For simplicity, once again the last 8 bits. Now look at the first operation, C equal to A ampersand B. Now when it comes to AND representation, what we do is, when we AND each of this binary digit, when both the bits are 1, then the resultant is 1. Otherwise, the resultant is 0. So here you see both the bits are 0, so the resultant is 0. Both the bits are 1, so therefore the result is 1. Again out here 1 and 0 is always 0. Only remember, for AND, only when both are 1, the output is 1. So 0 and 0 is 0. 1 and 0 is 0. 0 and 0 is 0. 1 and 1, once again 1. 0 and 0, still 0. So it's almost like multiplication, you see. If you observe carefully, it is almost like multiplication. Now, this is what gets stored inside C. So now what we do is, we go for the decimal representation to understand which decimal number got stored inside the variable C. So this is 0 into 2 to the power 0. This is 1 into 2 to the power 1. This is 0 into 2 to the power 2. This is 0 into 2 to the power 3. 0 into 2 to the power 4. 0 into 2 to the power 5, 1 into 2 to the power 6. So this happens to be 0, this is 2, this is 0, 0, 0, 0, this is 64. When we add this all up, we get 66. So when we add it, 66 gets stored inside the variable C. So here the value of C is 66. Now what we are going to do is, we are going to perform the OR operation. OR operation will involve when either of the bits or both the bits are 1, then the resultant is 1. So if any of the bit is 1, then the result is 1. If both the bits are 1, still the result is 1. So if we have 0 or 0, this will result to 0. 1 or 1 will result to 1. 1 or 0, 1. 0 or 0, 0. This is 1, this is 0, this is 1, this is 0. Now what we are going to do is, we are going to convert this to decimal. So we have 0 into 2 to the power 0. We have 1 into 2 to the power 1. We have 1 into 2 to the power 2. We have 0 into 2 to the power 3. Here we have 1 into 2 to the power 4. Here we have 0 into 2 to the power 5. Here we have 1 into 2 to the power 6. So this results to 0. This is 2. This is 4. This is 0. This is 16. This is 0. This is 64. So what we get is 86. So the value of D is 86. Okay. Now we are going to do the XOR operation. So E equal to A XOR B. Now in a XOR operation, what happens is, this is very interesting. Here what happens is, if both the bits are same, then the resultant is 0. Otherwise the resultant is 1. Now see over here, both the bits are same. It doesn't matter whether it is 0 or 1. If both the bits are same, the resultant is always 0. So both are 0, so therefore 0. Both are 1, still 0. One of them is 1, the other one is 0, so we'll go for 1. This is 0, again 1, both are same, so therefore 0, this is 0, this is 0. So you see how simple is XOR. Now once again, using the usual method, we'll convert it to decimal. So 0 into 2 to the power 0, this is 0 into 2 to the power 1. This is 1 into 2 to the power 2, this is 0 into 2 to the power 3, this is 1 into 2 to the power 4. So we get 0, this is 0, this is 4, this is 0, this is 16. So when we add up, we get 20. So the value of E is 20. So this is how the AND, OR and XOR bitwise operator works. Now we are going to see the NOT operator. Now we are going to find out how the bitwise operator works with the NOT bitwise operator. Now you see, the NOT bitwise operator works with a single operand. That is, we have only the variable A out here, and this is the tilde symbol. The name of this symbol is tilde. It is used as a NOT operator in Java. Now A, which happens to be 14. Now when the NOT operator is used, what is the value which gets stored in B? Now this is very interesting, and it is concerned with the 2's complement. Now you see, the value of A is 14, so I have already found the binary representation of 14. That is, A is 14, and the binary representation of 14 happens to be 1110. For simplicity, we write the last 8 bits. Then what we have is B, which is NOT of A. Now when it comes to NOT, it's pretty simple. It's almost like, in fact, not just almost, it's completely same like 1's complement. That is, convert all zeros to 1 and 1's to zeros. So this will become 1, 1, 1, 1. This is 0, 0, 0, and this is 1. So you can see all zeros got converted to 1 and all 1's got converted to 0. Now this is the binary representation of the number which got stored inside B because of the NOT bitwise operation. However, there is a problem out here. The problem is the extreme leftmost bit, you can see over here, happens to be 1, which indicates it's a negative number. Therefore, what we are going to do is, we are going to go for 2's complement method to understand which negative number got stored inside variable b. So for 2's complement method, first thing what we need to do is find the 1's complement. So let's find the 1's complement. So 1's complement, this will become all reverse, 0, 0, 0, and then 1, 1, 1, 0. So this is 1's complement. To get the 2's complement, what we do is we simply add 1. Now what do we get? 1, 1, 1, 1, 0, 0, 0, 0. Now we convert this to decimal. So 1 into 2 to the power 0 using the usual method, 1 into 2 to the power 1, 1 into 2 to the power 2, again 1 into 2 to the power 3. So this happens to be 1, this is 2, this is 4, this is 8. When we add this up, we get 15. So the value inside B is minus 15. Why minus? Because we had a 1 at the extreme leftmost end. This is what happens. So I believe you can understand how this bitwise NOT operator works. Now we'll go for a negative number and we are going to check how the bitwise NOT operator works with a negative number. So what I'm going to do is I'm going to take minus 14 out here, and now we are going to use the 2's complement method to understand how minus 14 got stored inside variable A. So 14 is actually 1110. Again, the last 8 bit for simplicity. This is 14. Now for representing minus 14, we have to use 2's complement. For 2's complement, first go for 1's complement. So 1's complement will be reverse the bits and add a 1 to the 1's complement to get the 2's complement. Now you can see 1 plus 1, 0, carry over 1. I believe you remember which I had said earlier. So 1 plus 0 is 1, this is 0, 0, 1, 1, 1, 1. So this is what minus 14 is. Now what is written is B is equal to not of A. B equal to not of A. That means we are going to reverse all these bits. That is complement these bits. So this will be 0, 0, 0, 0, 1, 1, 0, 1. Now you see the extreme leftmost bit is 0, indicating that it's a positive number. If it is a positive number, do not go for any 2's complement method. We can directly convert from binary to decimal. That is 1 into 2 to the power 0. This is 0 into 2 to the power 1. This is 1 into 2 to the power 2. This is 1 into 2 to the power 3. So we get 1, this is 0, this is 4, this is 8. So we get 30. So this time the value of B will be 13. That is positive 30 because we got a positive number because of the extreme leftmost bit was 0. Now we are going to learn about shift operators. And we'll begin with the left shift. And you can see what I have done is I have taken a variable 19, and inside B what I am doing is A, which is 19, left shift 2 bits. Now left shift 2 bits. What do I mean by that? First of all, we'll go for the binary representation of the number 19 because that is how internally 19 gets stored. So the binary representation of 19, which is A, happens to be 1, 0, 0, 1, 1. So for simplicity, 8 bits I have taken. Now remember, all the 32 bits, the remaining 28 bits, I have written only the last 8 bits. The remaining 28 bits on the left hand side are all filled up with 0. Now what I have written is B equal to A left shift 2. So what you can imagine is the entire number gets shifted 2 places towards the left. So what is the resultant? The resultant is, since I have gone for left shift 2, that means 2 bits from the extreme left end will simply get out. The entire number gets shifted 2 bits towards the left. And the resultant is the first two bits will simply get out, and at the vacated space on the right hand side, it will always get filled up with 0. So if this is the situation, this two zeros is going to get out. So what we are left with is 0, 1, 0, 0, 1, 1. You can see these two bits are gone, and we are left with the remaining bits, that is this bits. And on the right hand side, we are getting two vacated bit space, so it will always get filled up with 0. So this is what happens with left shift. Now once again go for the conversion from binary to decimal to understand which number got stored inside B. So this is 0, this is 0, this is 4, this is 8, this is 0, this is 0, this is 64. So we get 72 plus 4, 76. So the number 76 got stored inside variable B after 2-bit left shift. So this is what happens with left shift operator. Now this time I have just reverse the shifting, that is towards the right. I have taken the same number, that is 19. So how does it work? A is equal to 19, and the binary representation of 19 is 1, 0, 0, 1, 1, and we'll take only the last 8 bits. So this is the last 8 bits of the number 19. Now what is written is B equal to A right shift 2. So what we are going to do, exactly the same thing what we have done with left shift, but this time from the right hand side, since I have written 2 bits are going to get out. And on the left hand side, it depends upon if the number is positive, on the left hand side, you will get zeros getting filled up on the vacated spaces. And if the number is negative, 1 will get filled up on the vacated spaces. Unlike the left shift, in left shift, on the vacated spaces on the right hand side, it was only 0 getting filled up. Whereas with right shift, on the vacated spaces, on the left hand side, you will get always, it retains the sign. That is, if the number is positive, zeros get filled up, and if it is negative, only ones get filled up. Now look at this, A right shift 2. So 2 bits from the right is going to get out. So we are left out with 0, 0, 1, and then followed by this 3 zeros. So there are 2 zeros, 2 vacated spaces remaining over here. You can see, I can just put an underline. So 2 vacated spaces. Now you see, look at the number 19. It is positive. Since it is positive, this 2 vacated spaces will get filled up with zeros. So it's that simple. Now we'll go for binary to decimal conversion to understand which value got stored inside variable B. So we get 4. So with right shift, we get the value 4 getting stored inside variable B. Now what we are going to do is, we are going to try out a negative number right shift. So let's take minus 19. Now 19, which happens to be 1, 0, 0, 1, 1. This is 19. Since it is negative, we'll use 2's complement method to understand that a negative number is represented using 2's complement in Java. So first of all, we'll go for 1's complement. That is the requirement. In 1's complement, we simply reverse the bits. And for 2's complement, we are going to add a 1. So we add a 1. This is pretty simple. 1, 0, 1, 1, 0, 1, 1, 1. So this is our minus 19, which got stored inside the variable A. Now you can see the extreme leftmost bit is 1, indicating that it's a negative number. Now what we are going to do is, we are going to make a 2-bit right shift. So these 2 bits are going to get out. So we are left out with 1, 1, 0, 1, 1, 1. And we have 2 vacated spaces. Now as I said earlier, that when it comes to right shift, it always maintains the sign. So since it was a negative number, it will get filled up with 1s out here. Had it been positive, it would be 0. Since it is negative, 1s get filled up on the vacated spaces. Now this is what gets stored inside variable B. Now don't jump into conclusion that this is the number, so we'll go for binary to decimal. No. The extreme leftmost bit is 1, indicating that the number is negative. So we are going to once again go for 2's complement method to understand which number got stored inside variable B. So for 2's complement, once again first go for 1's complement. Simply reverse the bits 0, 0, 0, 0, 0, 1, 0, 0. And 2's complement is simply adding 1. Now this is the negative number which got stored inside B. So this is 1 into 2 to the power 0. This is 0 into 2 to the power 1. This is 1 into 2 to the power 2. So we have out here 1, this is 0, this is 4. So this adds up to 5. So the value of B will be 5. This is how the right shift occurs with negative numbers. Now we are going to go for the unsigned right shift, and this time I've taken the same number, that is 19, and if you look at the name of this particular operator, unsigned right shift, that means the resultant is always without the sign. That means it is always positive. That means unlike the normal right shift which you had learned earlier, it always maintains the sign of the number. That is, in the vacated spaces, if it is a positive number, it gets filled up with 0. And for negative numbers, it always gets filled up with 1. Here, since it do not maintain the sign, it will always get filled up with 0, irrespective of whether the number is positive or negative. On the vacated spaces, we will always get 0 getting filled up. So first of all, we'll try with the positive number, and then we'll see with the negative number what is the resultant. So here we have a number, say 19, and the binary representation of 19, I've already done that before, is 10011. So this is what happens. Okay, so now B equal to A unsigned right shift 2. Now, from the extreme rightmost end, we are going to remove 2 bits, and we are left out with 0, 0, 1, 0, 0, 0. And this time we have 2 vacated spaces. And since it is unsigned, irrespective of whether it is a positive or negative number, it will always get filled up with 0. That's it. So, with positive numbers, the unsigned right shift behaves the same way as signed right shift, that is simply right shift. So here we have 0 into 2 to the power 0, here we have 0 into 2 to the power 1, here we have 1 into 2 to the power 2, that is 0, 0 and 4. So the value of B will be 4. Now this time I have taken a negative number, that is minus 19, and here we have A equal to minus 19. So first of all, we'll use 2's complement to know the representation of it inside the variable A. So here we have 19, which happens to be 10011. So we'll use 2's complement. So first go for 1's complement, that is reverse the bits. Now we'll go for 2's complement, that is add a 1. And addition is pretty simple. And this is what our negative 19 is represented. Now, what is written is, now remember, all the remaining, this is only the last 8 bits, the remaining 28 bits are all filled up with, 1. So here we have 8 bits followed by remaining 24 bits, which are all filled up with 1. So here what I have written is B equal to A unsigned right shift 28. So that means all 28 bits are going to get out of this entire representation. So we'll be left out with the last 4 ones, because the remaining all these bits on the extreme leftmost end was filled up with 1. So if 28 bits gets out, we are left with the last 4 ones, and these are all the vacated spaces. That means the remaining 24 bits are all vacated. Now, as mentioned earlier, unsigned right shift do not maintain the sign. That is, irrespective of whether the number is negative or positive, on the left hand side, it will always get filled up with 0. So, we'll be left out with all zeros on the extreme leftmost end. So, this is the number which got stored inside variable B. And this is simple. Since it is a positive number, we can directly go for conversion. So the value of B will be 15. So this is how unsigned right shift operator works.